Thank you, Tim, for an introduction, and thank you for the organizers for giving me the opportunity to talk here. It's a pleasure to be like in an in-person conference. It's been kind of a while. Okay, so let me get underway. So let me write the title. Yeah, can everybody see, or should I write bigger? Okay. Okay. For the first part, it will be a little bit of history, and then I'll get into joint work. So the first part is, the history of the problem I'm going to talk about. So I'm going to present some results, and then the second part is joint with Lior, Berry, Soroker. And Orben, Porat, where we focus on a particular case of the problem I'm going to describe. So what are we interested in? So we're looking at the following thing, which are polynomials, x to the n plus an minus 1, x to the n minus 1, plus a1x plus a0. And there are two regimes. You can study the question in probabilistic Galois theory. There's the so-called, so there's the first regime, let's call it A, which is mostly going to be most of the talk. Okay, so this is the large box model. Okay, so in this large box model, what you want to do is you let your AI range in the interval minus h to h. And then maybe I should have introduced a notation here. So G of f is going to stand for, sorry? Okay, perfect. Okay, so this is the Galois group of the polynomial f. Okay, so that's that. So I'll write a little bit bigger. So the AIs are in minus HH, and we want to understand the behavior of the group GF. Okay, so that's the question in both of the regimes. And then the other one, this is called large degree. And restricted coefficients. And for this one, what happens is, here I should say, I'm letting the height go to infinity. That's an important thing because this is asymptotics and probabilistic thing. And then for the large degree and restricted coefficients, I'm studying this regime. When the degree now goes to infinity, the AIs are independent random variables. So there. And they're integer valued. Okay, so. And for simplicity, so I'm going to briefly say a little bit about the second part. So for simplicity, I'm just going to take them to be uniform in some small set of integers. So let me just say a little bit about 2. So this part, yeah, maybe I should have said here B. Okay, so let me say a little bit about part B. So I'm going to take it to be uniform, and so there's an old conjecture of Odlyko and Poonen Okay, so, and n is going to be my set of values. So this is for uniform, this is the set of values. So if I take n to be 0, 1, and I also assume that, let's not take trivial things. So you need to take A0 to be 1, otherwise, everything is also not an interesting question. Then the conjecture, so with high probability, which means that as n goes to infinity, the probability in the limit should hit 1. F is irreducible. So. Okay, so what do we know about this? So this, so let me say a little bit about this regime. So this is a recent result, and then I'll talk about unconditional ones. So this is actually, let me just say this is 2019, and this is conditional on the generalized Riemann hypothesis, or the Riemann hypothesis for Dedekind zeta functions. Okay, so there are some number fields involved, and you need to know the Riemann hypothesis for those Dedekind zeta functions. So they show even more. So they show that this is, as long as you have at least 2 elements, and then you don't take trivial things. Okay, so then the probability that actually F is irreducible this is indeed 1 as n goes to infinity. And moreover, you can say even what the Galois group is, except that you can't distinguish between Sn and An. So GF, probability that the Galois group is not one of these two, this is going to be little O of 1. Okay, so that's one conditional one, but there's 2 unconditional results. So yeah, do you have a question? Okay. Okay, great. So there are 2 recent also unconditional ones. So there's, the first result is by Berry, Soroker, and Kozma. So again, there's more general setting, but again, I'm restricting to uniform. So in this one, if you take the set n to be 1 to 210, or something that's equidistributed mod, the product of, product of 4 primes, then it works. So they show this one. So it's unconditional. So you get the same result here and the same thing here. So I'm not going to write it twice, but you get, again, the probability that this is irreducible, and then this 2 things unconditionally. And recent work with, so again, the same people. Okay, so this is, let me just save some room for writing. So this is plus Koukopoulos. So hopefully I'm not spelling anything wrong. Okay, then you can do any, so you can do any 1 to h for h bigger than 35. So you can show, the same result as long as you have at least 35. So the methods involved here are more, probabilistic in the end. So you reduce modulo prime, and then you use random walk techniques and analytic number theory to get your hands on this. While, in the first question, there's a rather different, the methods are rather different. But I wanted to at least give an overview of what's going on. Can I write on the back of this board, or should I use another board? How are people? Okay, so let me keep this one up because I'm not going to use, the B part is done. So as I said, most of the talk is going to be spent in A land. So let me give you a little bit of history. So this is an old question due to van der Waarden about the study of these Gala groups. And he showed that, basically, let me write it in the probabilistic version. The probability that your Gala group is not actually Sn, so he was the first to show some power saving. So this is O of H, and then you have some small saving here. So I'm going to write it n minus 2, and then, log H. So basically, it's like in a fair world, you would expect the Gala group always to be Sn, and this indeed, is the case. And actually, he conjectured, so this is his conjecture, he actually conjectured that you should do better. So the probability that the Gala group of your random polynomial in the large box model is not equal to Sn should be little o of h to the minus 1. Okay, so that's van der Waarden's conjecture. And now I'm going to go briefly through the history of the problem. And, so the first person to actually improve a little bit, so I'm not going to write explicitly, but the first person to improve was Knobloch. Is not a big improvement, so I'm not going to write exactly what it is. But the first substantial improvement was done by Gallagher. So this is in 1973. So he showed that this probability that you don't have the full symmetric group is O of h to the minus 1 over 2 plus epsilon. So the method here is basically a large sieve. So I'm going to briefly write what you use. So this is a large sieve where you study the behavior modulo mod primes. So you look modulo small primes. Okay. And then, it took a long while for this to actually get improved from minus 1/2 plus epsilon. So here I am not very precise. He actually did h to the minus 1/2 times some log factor, but I just wrote it as an epsilon, for convenience. Zwina in 2010 basically removed the log factor from that equation. So this is O of h to the minus 1/2. Okay, and then Dietmann was first to break, this deadlock of minus 1/2. So to go below minus 1/2, so this is this one. So this is G of f is not Sn. This is O of h. And now, you have to do your computer work, but this is roughly minus, 0.61. So it's better than minus 1. Sorry, it's minus 0.68 something. Okay, so that's that. So this is 2013. And he showed something more. So since I'm going to be focusing a lot on this later, he showed that actually if you don't do An or Sn, so GF is equal to, I should have written it the other way around. So the probability that you hit a certain group which is not An or Sn, you can actually control it in terms of the index of the group. So namely, this is close to what you expect from van der Waarden. So this is -1, and then you have to add up the small fraction, which is the index of the group. Okay, so this is the index of the group in Sn. Okay. Okay, so that's was 2013. And what I would say is that mostly what he used is the determinant method, and then resolvents for Galois groups. Okay, so the determinant method is a classical way to study rational points or integral points on varieties, and then the extra input is when you have a certain Galois group, you have a resolvent which tells you if you're inside that specific group. So the resolvent helps you to decide if that happens. Okay. And then again, it was a bit of a break until 2018 when you had specific results in small degrees. So I'm not going to write them explicitly, but Chow and Dittmann, they completely solved the problem for n equals to 3 and 4. So this is 2018. Okay, and then this year we got a lot of new results. So the first one was the same two people, Chow and Dittmann, announced that, okay, so this is same people, and this is 2021. So again, this is the probability that you're not hitting Sn or An as the Galois group. So this is O of H, and this is 1 minus 1, 0, 1, 7. And this is as long as n is bigger than 3, and you're not one of the three numbers, 7, 8, or 10. Okay. So again, maybe, because this will be the focus of the talk in a few minutes, An. So An remains as the question, what really happens, for An. And then there was another group of persons. So this is Anderson, Teresa Anderson, Gaffney, Lemke Oliver, Lowry Duda, Shakan and Zhang. So I think this one, was a little bit before they posted this paper. So they showed worse. So this is, sorry, they showed better than Dittmann's result from 2013. So basically, this lowers the An probability. Okay, so they showed that you can do better than the minus 0.68. So this is minus 2/3 plus 2 over 3n plus 3, and then plus epsilon. Okay. Yeah, so I think, I was getting my numbers wrong. So yeah, square root of 2, you should be really careful what it is. It's like 1.42. So I was saying 0.6, that's 0.58 there, and this is 0.66. Yeah, so yeah, this is a little bit an improvement on Diedman's result from 2013. And, the amazing thing is Bhargava actually, so these are actually preprints, and Bhargava actually announced the proof of van der Waerden's conjecture, so almost the full van der Waerden conjecture, except that, so this is, be careful about the O, this is O of h to the -1 plus epsilon. So this is almost, again, this is this year. So h to the -1 plus epsilon. Okay, and let me say a little bit about the methods. So the method here, that's why the method here is the same as in the paper from 2013. Again, the determinant method plus carefully thinking about rational points on varieties. This one is on improvement on the sieve. So it's an improvement on Gallagher's method, doing the sieve more carefully. And Bhargava's result is very, very different. It's a really, really clever trick to actually show the result. So let me focus a little bit on what actually he did, because we're going to split off and pose a conjecture. So the way this happened is you need to split off into two categories of groups. There's these groups, GF, which are imprimitive. And for the imprimitive ones, this is the same as saying that your extension has a non-trivial subfield. So and Martin Whitmer actually showed something very strong. So you can put all of these imprimitive ones. So let me just write it here that GF is imprimitive. Let me write it like this. This is going to be O of h to the -n/2 plus 2. So it's almost the square root, almost square root kind of cancellation for this. And then, you have the question, what happens actually for primitive ones? So let me say a little bit. So basically, Bhargava dealt with these kind of cases in a clever way. So let me connect because I want to write a conjecture, let me connect this to another conjecture. So let me tell you actually what we expect to be true when you have primitive ones. So what really happens when G is primitive? So let's just stick to this case and try to understand it a little bit better. And this will motivate what we're trying to do in our paper. So Lemke, Oliver, and Thorne actually had an earlier paper, which is quite interesting. So up to that point, people didn't think too much about the connection. So there are two different worlds. You can think about the discriminant of the polynomial, we can think about the number field it actually generates. And the difference between these two discriminants, is up to a square. So in their paper, they connected, connected basically Male to this to the question of van der Waarden. So I'm going to rephrase a little bit one of their theorems just to give you an idea of what to expect. Okay, so let me just write one version of Male's conjecture, which is the weak version, but let me write some notations here for people who haven't seen Male's conjecture. So let nxg be the following set. So this is, the following counting function. This is the number fields E with the following properties that, the degree of the extension is n. The Galois group of the closure over Q, this is isomorphic to G, and the discriminant of the number field, this is less than X. Okay, so that's one quantity. And then for G, an element in our Sn subgroup, we're going to define the index of G. So I'm going to write the easiest definition possible. This is n minus the number of cycles of G. Okay, and then the following quantity A of G is just going to be the minimal such index. As long as G is not 1. Okay, and the weak version, so this is so the weak version is like this. You expect the quantity n of xg to be less than x to the 1 over ag plus epsilon. Okay. So again, there's more precise version, but I won't get into that because that's a really cumbersome one and there's some issues about it. So the version is with x 1 over ag, and then there's a log factor, but there's issues about the power in the log factor there. And what's the connection between Male to van der Waarden? So one of their theorems shows the following thing. So if we know Male, then we expect less than the following number. So this is h to the a times g. And here, maybe I should say that again. Let me put this caveat here that this is really important. So, because there's a different version when you don't assume it's primitive, but it's not quite that different. So you expect this to be true. Okay, so, and their theorem actually says something better. You don't need to know it necessarily for A of G, but if you know something like this bound for some exponent here, you can plug in that exponent and make it work. Of course, this doesn't help for AN, but the interesting thing is once you're not equal to AN, so so we expect polynomials, so F with Galois group G, so this is with GF isomorphic to G. Oh, sorry, I didn't write it completely. So we expect this count of polynomials with actual Galois group to be G. to be less than this quantity here, A of G times 2n minus 2 plus 1 minus 2n plus epsilon. And now a little bit of group theory. So actually, this is just a little bit of group theory. So let me actually drop this down. Yeah, so if you know Male, that gives you that upper bound. So their theorem actually shows that if you know Male, or you know something like an exponent in Male. So you don't need to know the full strength of Male, but here I'm just going for the full Male conjecture to tell you actually what do we expect to happen. Yeah. So basically, you can take the exponent in Male and just multiply by 2n minus 2, and you would get it to work for van der Waarden. Okay. Yeah, do you have a question? So for AN, that's going to give you, basically it just gives you 1/2, okay? And then you just get h to the n minus 1 plus 1, that's h to the n, minus 2 over n, that's really bad, worse than any saving. So that doesn't help you for that, but let me tell you actually what it helps with. Well, as long as G is primitive and this is not equal to AN, this is just a small group lemma that's inspired by a paper of Berry, Sorokar, and Kozma. So that's the initial paper I cited where they had the 1 to 210. You can show that, so G primitive, actually, let me write it. And let me write also Sn here, not to make any wrong statements. You can show that A of G, this number, is going to be very big. So this is at least square root of n minus 1 over 4. Okay. So in the end, as long as n is big, so here I didn't do my numerics, but I think at least when n is bigger than 49, you would, so this would imply that for G not equal to AN Sn, n primitive, they are fewer than h to the n over 2 polynomials with such a Galois group. So. Okay, so what does it really mean is like, if you want to refine a little more van der Waarden's conjecture, well, most of the talk has been about, the transitive, so let's stick to transitive groups. I mean, assuming F is irreducible. That means most of the error term is coming to the question mark, what happens with the alternating group, really? And then there's this thing about the imprimitive ones, but actually this result of Martin is a little more precise. Like, you can factor your n as A times B, and then you get an H to A plus B. So it's n minus A, it's minus n plus A plus B, I think, the saving. So really, I think if you put it all together, so there's two groups that, so if you are able to do it on a computer, basically what I'm saying is that the error term should mostly come from this G equals to AN, and maybe the other one that remains as a question mark is the read product of the cyclic group on 2 elements. So let me write it like this, with Sn over 2. So really, these two groups should be the error term. Okay, and now let me actually get to talking a little bit about the AN and what we can show about the AN. So we can't prove any upper bounds, but there's lower bounds that we construct for this one. Okay, so let me focus on the G equals to N. Okay, so this is the part B. And now there's a very easy criterion. If your Galois group is An, that means your discriminant. So this is the first observation is then the discriminant of the polynomial. So let's call it delta f is a square. Okay, so let me just write it this way. So, so one question you can ask, and we don't have an answer to it, is okay, if you condition on the discriminant being a square, you should expect that the Galois group is as large as possible, but we don't know that. So the first question you can ask, and we don't have an answer to it, is you should expect that, you know, the probability that discriminant of f is a square should be roughly asymptotic to the probability that so An should dominate. So what we're saying on this variety is that most of the integral points you see on this variety, if you cook up again your polynomial, you expect it to have Galois group An. So we don't have an answer for it, but that's an interesting question to think about. What we do have, so the first result is we can show a lower bound, and this matches a construction, so a very similar construction of, and I think it's a little bit better maybe in one case, but we haven't checked it. So it's the probability that GF is An. So with this notation is bigger than O of H to the R minus N. Or in other words, we construct a family with roughly H to the N over 4 elements that has Galois group An. Okay, and the second part, this is also not a complicated, so this is an interesting construction. But on the other hand, you can guess that if I focus on that group there, which is, oh, sorry, so this is, yeah, Sn over 2. Okay, so if I do GF is C2 REIT Sn over 2, and then I intersected with An. This is at least H to the minus N minus 1 over 2. Or in other words, we construct a family with, so here we construct a family with H to the N over 4. So let me just write, so this is roughly H to the N over 4. And here we construct a family with roughly this many elements, which has Galois group this intersection here. And now if you expect the question 1 to be true, then what you would expect about the Galois group being An is you at least expect a lower bound of H to the N over 2. So, and we actually conjecture, so let me, I mean, we don't have pretty much good evidence, but again, Igor Rivin, I think in 2015, wrote a similar thing. So the conjecture is that actually the probability that you actually get the Galois group to be An, this is at least H to the N minus 1 over 2. So, and so we expect H to the N over 2 polynomials to have Galois group this. I mean, the issue with this is like, when I wrote this part here, you would like to maybe do some, you know, computer verification, but because N is so large in this case, so as I said, you probably need to take N here to be at least 49. And then you probably need to take it even larger to see some sort of error term that's meaningful. Yeah. So right now for this part here, I mean, there's not yet a very good reason, but we suspect it to be true. Okay, so that's that. Okay. So as I said, for this family, there's a similar construction of, this is Landsman. Lemke, Oliver, and Thorne. Okay, so let me tell you what goes into the construction of the family. So for one, what we're going to be looking at is equation of the following shape. So you take f plus a times f prime is equal to h times the square of a polynomial. And here a and h are chosen suitably. So these are going to be at most linear polynomials. So these according to n mod 4. So we have to do a case-by-case analysis. So let me just do it for simplicity. Let me write the equation that we consider for n equals to 0 mod 4, because this is a very easy equation. So we just take the equation f plus f prime is equal to the square of a polynomial. Okay. So this is the equation for this one here. And after you take that equation, you think about, so the coefficients of G as independent, algebraically independent variables. So let's say that, n is 2k, then your G is going to be, x to the k, and then it's y to k minus 1, x to the k minus 1, plus y1x, plus y0. And your goal is to show that basically, if you consider GF over the extension, so let me call this vector of variables y. So you go over this extension, which is, so again, we can just stick to any field. So this is k, and then you do y, and then you do x. So you show that GF there is an. And then you basically use Hilbert irreducibility to specialize and get your result for the asymptotic. It's not complicated. So the steps in doing this is first you check that indeed, if you look at the equation, you would get correctly that discriminant is a square. But then, you need to do some checks. So the first check is you need to show that f is irreducible, which is not hard because it's quadratic in each of these variables, yi's. So then you can play around with the yi's. So you just do a computation of a quadratic polynomial. So going over this extension, it's easier because you have this flexibility that is quadratic in the yi's, so you can just specialize some of them to be 0. And then, so the argument is pretty standard, and then you just look at the different and the discriminant. Yeah, let me see how much time I have. So you look at the different and discriminant in an extension. You show both are the squares of a prime ideal, and that will tell you about the ramification of a certain map. So it will tell you that ramification indices are 2, so your Galois group is generated by 3 cycles. So, and then if it's generated by 3 cycles and it's transitive, then Jordan's theorem gives you that it's n. So it's not, it's a little bit computational. You have to actually do the computations. In each of the cases, n is 0 mod 4, 1 mod 4, and so on. But for 0 mod 4, it's a little bit easier. So, and once you do that, you get your Galois group over this extension to be n, and then you specialize. And you're done with that. And what's the second family? So let me maybe go there. So the second family So for the second case, yeah. Yeah. Yeah, and then you see in Mallet's conjecture, sorry, I messed up. It's 1 over AG. Okay, yeah, so I was writing it correctly, that one there. Sorry, it's 1 over AG. Yeah. Yeah, so let me just write it as a correction. So it's H to the 1 over AG, you're right. Yeah, 2n minus 2. Plus so on, okay, yeah. Okay, and for the second part, what's the family? Well, I'm going to write it this way. So your n has to be even. So you take the following family. So this is going to be, again, we take everything to be monic. So it's x to the n, and then this is going to be x to the n minus 2. And then I'm going to take here a coefficient, let's call it a n over 2 minus 1. And then, you know, a n over 2 minus 2, x to the n minus 4. And then it's a1 x squared. And then here you have to be a little bit careful. So just to make the discriminant a square, you need to take minus 1 to the n. And here you make, you make the fix a0 squared. Just to land inside the intersection with an. If I didn't put a square here, I just put a0, then you just get the read product of the cyclic group with Sn over 2. Okay, but if you make this one a square, that makes the Legendre symbol work. And there's your family, and it's not, again, hard to show. So this is the family. For example 2. Okay. Yeah, so again, it's a very interesting question. So again, I wanted to argue that kind of this AN question is the harder part of the conjecture, and understanding it would give, better understanding of, van der Waerden, the Aaron van der Waerden's question. Also, in part B, which I erased, we can't also distinguish in that question between the SN and AN in the probabilistic methods we saw there. So in the end, we need to understand better this. So the question is, what's really going on with this variety, which is, z squared equals to delta of f, okay, where, and we want to count, so we want to count integral points on this, so count. Again, where the height of f, so I don't care about the coordinate z, so this is like, Serre has this conjecture about cyclic covers for projective curves. So we want to understand, how many integral points do you get? And what we have here, is a family of roughly h to the n over 4 integral points on this variety. But the question is, how many do you expect? Or, in question B is how many points on that cube, which is 2 to the n, like the cube with 0, 1 vertices, how many points really do land on this one? Yeah. And obviously, the same construction applies, for the 0, 1 question. Like you can use the same kind of construction to do the 0, 1 question. Okay, so yeah, kind of the main punch of it is like we really need to understand better what's going on with this. And yeah, I hope, some of you would like to think more about this problem, because there's still a lot to be explored. And maybe what I would say, and I forgot to say it here, is that so conditionally on Mallet's conjecture, we would have that h to the square root of n something bound. So Bhargava can actually prove unconditionally. So for G primitive, he can get a saving of Cn over log n squared. So that's in his talk, so that he gave actually at the number 3 web seminar. So he can show something towards, that saving. I said but the saving is pretty strong if you assume Male. It's like you get to bound down to square root of n. So let me stop here, and if you have questions, I'm happy to answer them.
Thank you very much, Vlad. Does anyone have any questions? If Trevor Woolley was here, he would ask about the characteristic P analog of what you've talked about.
Yeah. So definitely that's something on my mind, to think about the function field analog and maybe get something better. So I think there are better bounds in this case here available, but I don't remember off the top of my head. I think at one point I was talking with Alexei Antin about this, but yeah, it's been a...
Well, at least I guess you also have the Q analog to think about. If that, if this problem is too hard in the function field setting, as it may well be, I guess you could also think about the Q limit as well. A bit more flexibility.